Well, this is our last official topic in AP Physics, and it's known as inductance, related to what we've just recently been talking about. We're going to investigate the nature of how a changing flux in one coil induces EMF and current in the other, and to the degree to which it does that, how efficiently it does that. And then we're also going to take a look at a single inductor and consider that it's inducing an EMF in itself because its flux changes within itself. So that'll be a very important component of our full understanding of these electromagnetic effects. I will now describe and define for you mutual inductance. So we start with two coils. And in the first coil we have a current. That current produces a magnetic field that's geometrically distributed as shown, essentially. And of course you see it goes through the second coil. So this is the magnetic field from current in coil 1. And then coil 1 has flux Pb1. And then there's Pb2 as a result of that magnetic field produced by the first coil. So a changing current, if you change that current, you're obviously going to change the flux. Changing flux in coil 2. The magnetic field is proportional to the current. More current, more B field. So therefore, the flux is proportional to the current as well. So Pb2 proportional to the current in number 1. Now the flux changes in coil 2, so therefore coil 2 says, I will produce an EMF. That is given by Faraday's law. The EMF produced in coil 2 is equal to d sub B dt, its changing flux, multiplied by the number of turns. So there's Faraday's law. Now the proportionality, we just stated that B is proportional to I1. Of course, that's obvious. Since that's true, then N phi B2 equals, since this is proportional to the B field, which is proportional to I, we're going to put a proportionality constant in here. We're going to call that proportionality constant the mutual inductance of the two coils. So that's our first introduction to this thing called mutual inductance. It's the proportionality constant between the flux in coil 2 and the current flowing in coil 1. To what degree is there a, say a significant flux in coil 2 based on the current in coil 1? You would have a greater mutual inductance, in brief. So let's look at M21, this mutual inductance between coil 2 and 1. It's just then, algebraically, number of turns in the second coil times its flux over the current. All right, so that's a little bit intuitive. There's greater coupling between these. If you, say, have a significant flux in the second coil, significant flux for a small amount of current. Small amount of current in the first one producing a large flux here means that these coils are coupled together tightly. Now if we reverse the roles of these coils, everything just flips. And we see that M1 to 2 equals M2 to 1. So the effect of that coupling is the same in both directions. So we're just going to drop the subscript and call it M, the mutual inductance of two coils. Basically, you can just sit them there in space next to each other and recognize this is a characteristic property of the geometry, the spacing characteristics of those coils. Now, M is equal to then, without the subscripts, N2 Pb2 over I1, and that's N1 Pb1 over I2. So there is the mutual inductance. And again, notice, in general, what's it related to? It's related to the number of turns, proportional to the number of turns, the flux in a given coil, and inversely proportional to the current in the other coil. So that is a measure of the mutual inductance, the coupling between those. Now let's take the time derivative, multiply both sides by I, bring I over, and then divide by dt. So like for the the first one here, we get N d phi sub b dt is m di dt. And we already know what N d phi sub b dt is, don't we? Yes, it's the EMF induced. So now we can say the EMF induced in number 2 is minus m di dt. di1 dt, of course. The rate at which the current changes in coil 1 is the EMF induced in number 2, but you multiply it by m. And m, very important, already includes the number of turns. So that's already included in there. So that's our result. And then, of course, we get the EMF induced in number 1 is minus m di2 dt, reversing the roles. The unit here is the Henry. It's a new unit for us. Well, what is a Henry? Well, certainly it's related to magnetic flux. And in fact, it's just a Weber per amp, or the flux divided by the current. So, makes sense how much flux you have per a given amount of current flowing in the other coil. That is the inductance between the coils. It's called the Henry. So now we're basically going to go through this again using an example of a solenoid. Turns N1, wrapped around by a larger coil, turns N2 of length L. We're going to determine the mutual inductance between those two coils. So the magnetic field in coil 1, the solenoid, that's just bunny. mu0 Ni, turns per length times the current in number 1. So turns per length is turns per length, N1 over L, big N1. And then the flux in the solenoid is the magnetic field times the area. And that's also the flux in number 2, because all of the flux that's inside the first coil is also within the second coil, this purplish looking coil. Okay, so all the flux goes through both. So that's really tightly coupled, isn't it? Well, the mutual inductance between those two is N2, the current that turns in number 2, times the flux going through it, divided by how much current is in number 1. All right, so that is N2. Phi B2 is just B1A because of what we just said. The flux in this outer coil is the same as the flux in the inner coil, which is B1A. So there it is, B1A over I. So that's N2 over I times B1, there's B1, mu0 N1 I1 over L, there it is, times the area. So carrying that out, we have the mutual inductance proportional to both the turns of both coils divided by the length and multiplied by A and mu0. Now, our next task is to determine the flux in each turn and the total EMF in the first coil, the solenoid here, as a result of the induced current in the second coil. So we change a current in the first coil. It induces a current in the second coil. The second coil then will have a changing flux, which induces an EMF and current in the first coil. So, now, when I say induce a current, maybe, maybe not. This is an iterative process in a way, so that one affects the other. So we're really just looking at the change in the second coil, the induced current in it, what it does in terms of producing an EMF in the first coil. That's what we're looking at. So, mutual inductance from 2 to 1, from the second coil to the first coil, is the number of turns in the first times its flux over the current in the second. Current in number 2. This can be kind of confusing, but repeat it if you need to get the idea of which one is which. And we've got the flux in the first one based on the current in the second one is what we're looking at. Whereas initially we're looking at 1 to 2, how much flux in the second one as a result of the change in the first one. Hopefully I haven't confused you more. Now, the flux in the first one, phi B1, is just then mutual inductance current 2 over N1. That is the flux in each turn of coil 1 as a result of the induced current in number 2. Now notice, so it says for each turn, well, mutual inductance already is a product of the turns of both coils. So you have N1, N2. We're dividing by N1. So we end up with the answer for the flux in each turn just related to the number of turns of the second coil. The more turns you have there, the more EMF or flux ultimately produced in the turns of the first one. Now, the EMF per turn then is just M over N1 here times the rate at which the current changes, di2 dt. Now you'll notice that the EMF per turn, of course, it's divided by N1, because again, we have the mutual inductance, which is the product of both. So it's really not dependent on how many turns. The EMF per turn in the first one is not dependent on how many turns there are. Because whatever flux is produced from the second coil in the region of the first coil is going through the first coil. So it doesn't have that, the answer to that has nothing directly to do with how many turns there are in N1. Because all the flux is going through each one. All right? So anyway, the bottom line is the EMF for the whole solenoid is the EMF per turn times the number of turns. Okay, now the end result is mutual inductance di2 dt, which is the result we got before. There's nothing new here. But M is proportional to the turns of both coils, so we see that ultimately the EMF induced in the solenoid from the changing current in the overlapping coil is ultimately proportional to the turns in the product of the turns in both coils. So I'm hoping at this point that you have a pretty solid intuitive grasp of the concept of mutual inductance.